All right, so let's start off with something like, sure. Let's see, this is Co-17B. Today is October 11th. And let's say we want to do the integral of x cubed times the square root of x to the fourth plus 7. Sure, let's make it, let's just do an indefinite integral. So when you see an integral like this, really, I should say, when you see any integral and it's not immediately obvious how to anti-differentiate it, you can't just find, it's like x to a power plus x to a power plus x to a power. You can't just use the reverse power rule. The first thing you should probably think of is, well, okay, I should say, the first thing you should think of is simplifying it and seeing if you can make it look nicer. And we'll do an example of that in a second. But the second thing you should think of is U-substitution. U-substitution is going to be like your favorite method of integration. At least I think it should be, because it's usually the nicest. Not always, but a lot of the time. So here, I'm thinking, well, what can I pick for you? There's a good choice here, and there's a not so good choice. And the good choice here is x to the fourth plus 7. And it's a good choice for two reasons. Reason one, it's stuck. It's inside the square root. That is almost always a good place to look, because it usually is the thing you want. Not always, but often is. The other reason it's a good choice is because if you take the derivative of it, the derivative of x to the fourth plus 7 is 4x cubed. And although I don't exactly have that, I don't care about being off by a constant multiple. We can always fix that. There's like 3 different ways of fixing this. Here's my preferred way. I would prefer to write this as 1/4 times du equals x cubed times dx. Other people do other things. Some people solve for dx and write dx equals du divided by 4x cubed and then replace the dx that way. That's not my jam. Other people do something like this. So I'll say those things later. Let's just do it the right way, and then we'll talk about the other ways. So now we're going to rewrite this integral. I'm going to point out that x cubed times dx, that is equal to 1/4 times du. And you should always start with changing the dx to du. That is the most important thing when you're doing U-substitution. So I'm going to write this integral as the integral of 1/4 times du. And then the stuff inside the square root, that's just u. So I've got the square root of u times 1/4 du. Let's do 2 things before we integrate this. And I think you should always pull out any constant multiples in front of the integral. So let's write this as 1/4 times the integral. And then we should rewrite the square root of u as u to the 1/2 power. Questions about how we got it? Okay, so now we've gotten to a place where we can find the antiderivative. We're going to use the reverse power rule, like we not almost always, but often do for integrals like this. So we're going to get 1/4 times u to the, if you really want, we can write out all the steps. U to the 1/2 plus 1 divided by 1/2 plus 1 plus c. I don't think you need to write that, but you can if you want to. It shows you know what you're doing. And then we should simplify this. It's going to be 1/4 times u to the 3/2 divided by 3/2 is multiplied by 2/3. 1/4 times 2/3 is 2/12, which is 1/6. And then since we started off with a variable of x and we're finding the antiderivative, right? It's not a definite integral. We're not finding a number. We're finding a function. The variable should be the same that we started with. So we're going to get 1/6 times x to the 4th plus 7 to the 3/2 power plus c. Questions, comments, observations? Okay, let's do a couple more. Let's look at something like, so I'm going to give you all this one. I want you all to make a choice for you on your own. So try starting, let's say this is problem 1. Sometimes I try to number the problems. I usually forget like halfway through. The integral, sure, x plus 3 over x squared plus 6x plus 1 squared dx. I want you all to make a choice for you and then find du dx. There's a good candidate for you and there's a less good candidate for you, but there are, in my opinion, two possible choices. Keep track of the time, James. Sure. Looks like most people made the choice of letting u equal x squared plus 6x plus 1, which is certainly the right choice, again, for two reasons. That thing is stuck inside the denominator being squared, and more importantly, really, I should emphasize the more importantly, its derivative is 2x plus 6, which is 2 times x plus 3. So I'm going to do this one in a slightly different way, just so you can see it, because some people do this a different way. If it were me doing this, I would do the following. Here's what James would do. James would say 1/2 times du equals x plus 3 times dx. And say that I have x plus 3 times dx, and that's going to be replaced by 1/2 du. But other people would do something else. Other people might just say du is equal to 2 times x plus 3 times dx, and then they would fix their integral. They would say, I'm going to rewrite this integral as 1/2 times the integral of 2 times x plus 3 times dx over x squared plus 6x plus 1 squared. That is also a valid thing to do. Have I changed my integral? No. I multiplied by 1/2 and by 2. That's valid, right? I multiplied by 1. But then this top part here, 2 times x plus 3 times dx, that is exactly du. Again, not what I like to do personally, but either way, we're still going to end up with 1/2 times du. So 1/2 times the integral of du divided by, oh, and then the bottom part's going to be u squared. I never like writing it like this, meaning I don't like writing du in my numerator. It just feels weird to me. You can certainly rewrite this as the integral of 1 over u squared times du. Or probably better, 1/2 times the integral of u to the -2 times du. That's actually how we should rewrite it, so we make it easy to integrate. And now we're going to, once again, use the, it's like so many times, it's the reverse power rule, the reverse power rule, it's all we like. So we're going to use the reverse power rule and get 1/2 times u to the -1 divided by -1 plus c. I would simplify this as -1/2 u to the -1 plus c, or -1/2 times 1 over u plus c. Oh, but I should actually plug back in what u is equal to. So really I should write this as -1/2 times 1 over x squared plus 6x plus 1 plus c. Again, I'll just re-emphasize that when you're finding an indefinite integral, right, where you've got no limits of integration, your answer has to be in terms of the same, variable that you started with. So if you're integrating a function of x, your answer better be a function of x. If you're integrating a function of some other variable, your answer better be a function of that other variable. On the other hand, definite integrals are a totally different animal. So I mean, not totally different. They're very, very similar. They're a little bit different. Not, I should not say totally different. They're a different animal, but not 100% different. So let's say we want to do, sure, this one here. The integral from 1 to the square root of 41 of x times the square root of x squared plus 8. And again, if you have questions or need me to clarify something, you should ask them because I'm sure you're not the only one. So when you have a definite question, yeah, Dan.
Start out the same way.
Yes,
Okay.
I usually am looking for, well, I should say, yes, I'm starting off either an indefinite or definite interval the same way as I'm trying to figure out how to anti-differentiate the function. The difference is for the indefinite integral in the previous examples, our final answer is the antiderivative. Whereas for the definite integral in this example, our final answer is going to be the value we get after we plug in the top minus plugging in the bottom. Okay, so U-substitution. There's a good choice for you. It's x squared plus 8. Again, it's the thing stuck in another function. It's the thing whose derivative is practically there. Du dx is equal to 2x. So 1/2 times du is equal to x dx. And great, I have an x times dx. I, for some reason, have gotten really used to rewriting this so that the things I want next to each other are next to each other. If you really want it, although I don't think you need to, you can write this as the integral from 1 to the square root of 41 of the square root of x squared plus 8 times x dx. Then it's just easier for me to write, oh yeah, x dx, always dealing with the dx change to du first. And there is a good reason for this, because sometimes if you're not careful this way, it's easy to accidentally grab the piece that you need for du in your U substitution. So I'll try and show you an example of that in a little bit here. My x times dx is equal to 1/2 times du. And my x squared plus 8 is equal to u. So when I rewrite this, and now I'm going to be a little bit careful here. This is going to be the integral of, I'm not going to write my limits of integration yet. It's going to be the square root of u times 1/2 du. Great, everything has changed to u. Well, not actually everything yet, because I haven't changed my limits of integration. There's a couple ways people like to do this. And most people, I think the better way is to change your limits of integration. So you could do this problem where you did the integral and then plugged back in u equal to x squared plus 8, and then plugged in x equal to the square root of 41 minus x equal to 1. But it's kind of a lot of going back and forth. The easier, more compact way is to actually change the values of u. So we know that u equal, we don't know, we decided that u is equal to x squared plus 8. So if u is equal to, sorry, apologies. If x is equal to 1, my lower limit, u is going to equal 1 squared plus 8, which is 9. And if x is equal to the square root of 41, then u is equal to the square root of 41 squared plus 8, which is 49. So those become my new lower and upper limits. And if I'm doing this, I like to be extra kind of explicit about it. I like to write in this step that this is x equal to 1 to x equal to the square root of 41. And in this step, this is u equal to 9 to u equal to 49. So that the person who's reading my work really knows that I have made this change. The great thing about making this change for a definite integral, you don't have to change back. So now I'm going to rewrite this as 1/2 integral from 9 to 49. 49 is not my favorite there, but oh well. Of u to the 1/2. And then we're going to do the integral. I should say the antiderivative. People use those terms interchangeably. You should get used to hearing people say one and meaning the other, but really, I mean, they're very interchangeable. We mean anti-differentiate when we say integral often. So we're going to get 1/2 times u to the 3/2 times 2/3 from u equals 9 to u equals 49. So here's what we get. 1/2 times 2/3 is 1/3. So I'm going to get 1/3 times, if I plug in 49, I get 49 to the 3 halves minus 9 to the 3 halves. And it would be okay to leave it like this. We shouldn't, because this does simplify, but technically this is a valid answer. But I really, really, really want to point out, I didn't go back and plug in x squared plus 8 for u, and then plug in root 41 for x and 1 for x. I just said, oh, I've already got things in terms of u, so I'm just going to stick with that. What's 9 to the 3 halves? What's 9 to the 1 half? Yeah. What's 3 to the 3rd? Right. So we're going to get 1/3 times something minus 27. Okay, what's 49 to the 3 halves? Well, what's 49 to the 1 half? Dana, I'm going to call on you. Oh, sure. What's 49 to the 1 half? Yeah, 49 to the 1 half. 7. What's, okay, 7 cubed is a little bit harder. 7 times 7 is 49. 49 times 7, well, 50 times 7 is 350. So 49 times 7 is 7 less than that, which is 343. Sure. Honestly, but that's how a lot of math tricks get done, is just seeing that this multiplication is close to this other thing. And if you do it and then subtract off however many you didn't have, that's where how you're getting. That's how a lot of people really do like fast, big math. Is they're like, oh yeah, I'm multiplying bigger things and then subtracting off a little bit. And then this is whatever. I don't know. Can I do the subtraction? No. 16, I think it's 316 thirds. But if I was a test situation, I'd probably stop right there. Honestly, I would stop there and then come back later if I had time. But stopping here, you have the right answer. It's just not as simplified as it could be. Doing this work is, assuming your teacher is grading in a way that we're giving you partial credit, which most people are, this work here is not worth a whole lot of points. This work here is worth the majority of the credit on a problem like this. Okay, let's see. I had some other things here. How much time? What? God, time just flies on by. Sure, let's look at one of these kind of harder ones. Sometimes U-substitution can be a little bit gross. Integral from 0 to 4 of the square root of 2 minus the square root of x. I'm still numbering things and pretending like I am, sure. 3, 4, yeah. So here, I don't really know what to choose. And the reason why I don't know what to choose is because I don't see a thing that if I pick u equal to it, its derivative is also going to be there. And sometimes you don't get that part, which is disappointing, but real. So we're going to make what I think is probably the only plausible choice here, which is letting u equal the inside of this larger square root. So u is going to be 2 minus the square root of x. And I will say it's not really worth our time to find du dx. You can, and so some people do it that way, but the easier way, when you can see that du dx is not going to be helpful, that's going to be negative 1/2 x to the negative 1/2, or if you prefer, negative 1 over 2 times the square root of x. That's not showing up anywhere in here. It's not helpful. So what we do instead is what's called, I think it's called a power substitution sometimes, but essentially you solve for x. So I'm going to take this here, I'm going to solve for x. So I'm going to add root x to both sides, and then subtract u from both sides. And then solve for x by squaring both sides. And then instead of finding the derivative of u with respect to the variable x, we're going to find the derivative of x with respect to the variable u. Or in other words, we're going to differentiate with respect to u. Well, great. We know how to differentiate something squared. Derivative of something squared is 2 times our something to the first, which I'm not going to write, times what? At this point, you all should know that when I say times what, the answer is the derivative of the stuff, right? Chain rule. Derivative of some stuff squared is 2 times your stuff to the first times the derivative of the inside stuff, which is -1. So then I can solve for dx here and say that dx is equal to, I'm going to say -1 times 2 is -2 times 2 minus u times du. And that's going to replace all of dx in this problem. So I'm looking all right. So if I rewrite this integral, I guess I should label things. I really don't want to write that there, but so here dx is going to be this massive thing. Dx is equal to -2 times 2 minus u times du. And the inside of the square root there, 2 minus root x, is just u. So I'm going to now have the integral of the square root of u, which we should really just get in the habit of writing as u to the 1/2. Right? Whenever you have a root and you know you're going to integrate, you want to write it as a power. It's just going to be easier. Times -2 times 2 minus u times du. And let's go ahead and change our limits of integration. If x is equal to 0, u is going to equal 2 minus the square root of 0. Sorry, I should write u equals, apologies, which is going to be 2. And if x is equal to 4, sorry, you would maybe like to see what I'm writing? Yes. U is going to equal 2 minus the square root of 4, which is 2 minus 2, which is 0. Notice we get an out of order integral. That's okay, that happens. It's totally fine. I personally would like to change it to be in the more normal order because it just feels better to me. So luckily we have negative signs that we can use for that. So I can totally rewrite this as the integral from 0 to 2 of the square root of u times +2 times 2 minus u. I really should have pulled that 2 out in front of the integral, but I didn't. Everyone see what I did there? Right? I said, instead of having the integral from 2 to 0 of a negative thing, I have the integral from 0 to 2 of the corresponding positive thing. Yeah.
Didn't you just make the whole thing negative?
I did. But the thing is, when you make a product negative, you're only going to multiply one of the factors by -1. So if I wanted to make, for example, if I wanted to make 3 times 5 times 7 times 8 negative, I'm not going to multiply each piece by -1. I'm just going to multiply the first piece or whatever piece you think you want. Right? That is the negative of that.
Okay.
So
You did that, it's hard to do.
right. So that's why I specifically singled out the -2 there, because like, oh, I'll just change -2 to +2. If you prefer, you can take the intermediate step of saying that this is equal to the negative integral from 0 to 2 of the square root of u times -2 times 2 minus u du. And then saying, oh, -1 times -2, or really pulling out the -2 in front and saying you've got the integral of 2 times the integral of 0 to 2 from 0 to 2 of. Now let's distribute the u to the 1/2. Not because we want to, but because we have to. There's no other way to deal with this. So u to the 1/2 times 2 is 2u to the 1/2. U to the 1/2 times -u is minus u to the 3/2. Now we finally get to find the antiderivatives. So we're going to get 2 times. All right, I'm adding 1 to the power dividing by the new power. So I'm going to get u to the 3/2 times 2/3. So I'm going to get 2 times 2/3 times u to the 3/2. I'm skipping the step of saying u to the 3/2 divided by 3/2 and just multiplying by the reciprocal. Minus u to the 5/2 divided by 5/2 is multiplying by 2/5. From 0 to 2. That looks terrible. So if we plug in here, I'm going to get 2 times 4/3 times 2 to the 3/2 minus 2/5 times 2 to the 5/2. That's gross. And then if I plug in 0, do I get 0? What's 0 to the 3/2? What's 0 to any positive power? Let's see, 0 cubed is 0 times 0 times 0 is 0. And then the square root of 0 is still 0. So 0 to any positive power is going to be 0. So when I think about plugging in 0 here and 0 there, I'm just going to get 0. So I'm not going to write that part. You could write -0, but let's just leave it like this. And this probably is about as simple as it gets because 2 to the 3/2 does not simplify nicely. The square root of 2 is not a nice integer number, so we're just kind of stuck with that unpleasant answer there. Okay, I think I had one more specific thing, and I should talk about that. There's so many things to talk about. Oh yeah, let's do that one. Sure. Let's find, yeah, let's do this. Where'd you go? Example, not you. Well, those are good ones. There's so many good questions. I could just talk about U-substitution all day, but let's not. Let's do the integral from 1 to 4 x squared over 1 plus x cubed dx. All right. Our choice for u here is going to be the denominator. Our du, let's see, 5, sure, is going to be 3x squared dx. I will point out, most of the time when people do a u-substitution, they don't write du dx equals the derivative. They go straight to writing du equals the derivative times dx. And then I'm going to adjust by multiplying both sides by 1/3. So 1/3 du equals x squared dx. Now we start rewriting. I like to say, oh yeah, there's my 1/3 times du. There's my u. So here I'm going to get 1/3 du on top, u on the bottom. Let me not change my limits of integration this time, just to show you how it goes if you don't do it that way. So if I'm not going to change my limits of integration, there's one of two things you can do. There's probably one thing you should really do. You should probably write them still, but point out that you know that those are x values, not u values. If you just write 1 to 4, it is wrong. Because you're saying, I think u equals 1 and u equals 4, but we know that that's not the case. U would be 2 and 65 if you plugged in x equals 1 and x equals 4. But we're not going to do it that way. We're going to change it up. So then we're going to rewrite this as the integral from x equals 1 to x equals 4. You do need to write that every time until you get to the place where you change it back to x's, which is kind of annoying, which is why I don't usually do it that way. Put the 1/3 out in front, have a 1 over u du. Okay, help me out. What's the antiderivative of 1 over u? Yeah, natural log of, yeah, from x equals 1 to x equals 4. I don't need a plus c, right? No plus c necessary for a definite integral. And then we're going to get 1/3 natural log of, we're going to plug back in what what u is actually equal to, which is 1 plus x cubed. From x equals 1 to x equals 4. I don't need to write the x equals part anymore because we know it's x because we've got x's back. And then we can plug in and get 1/3 times the natural log of 1 plus 4 cubed is 1 plus 64, which is 65. And I'm not writing the absolute value because the absolute value of 65 is 65. Right? If your number is positive, you don't need to write the absolute value. If your number is negative, you can just write the corresponding positive number. Oh. Thought you had a question there, Tasia. Minus 1/3 the natural log of what? And if this was your answer, that would be totally fine, and I would leave it that way. But you might, if you're looking up if this was a question in a book and you wanted to check to see if your answer was right, the way the book would probably write the correct solution is as 1/3 times natural log of 65 minus natural log of 2, which they would then simplify further as 1/3 times the natural log of 65 divided by 2. Just be aware that that's often the simplification people are going to make. Where did I get the 2? So when I plugged in 4, I got 1 plus 64. Right. When I plugged in, I got 1 plus 1. Yeah, right.
Oh, why is it now the other problem? We changed the balance, but on this one, we got the same.
Because I'm showing you a different way of doing it. You could do it either way. So just let me point out, we could have also, instead of doing this, we could have done this instead. We could have said, I don't want to do that. I want to do it the better way that we've been doing. So the other way you could do this is say, well, I am going to change my bounds. If x is equal to 1, everybody, what's u equal to? 2. And if x is equal to 4, What's u equal to? Right. And then I just got 1/3 the integral of 1 over u. I integrate, I get 1/3 natural log of the absolute value of u from u equals, oh, sorry, you all said 2 and I wrote 1. I apologize. From u equals 2 to u equals 65. And then if we plug in, we get 1/3 natural log of 65 minus 1/3 natural log of 2. The same answer. It's a perfectly valid way of doing it this way, but it, in my opinion, takes up a lot more mental space than actual physical space. So I would always encourage people, with some exceptions, but I would almost always encourage people to change your limits of integration. There are times when finding the change limit is kind of a terrible pain in the butt, specifically with trig stuff, but usually it's worth your while. So I would always encourage you to not do it this way, but to do it this way. But some people like doing it this way better. So it's fine to do it this way. You're doing more work in my opinion, but if that works better for you, you should do it that way. You should do it the way that works best for you, as long as it's right. That's almost always my opinion on. I mean, I will tell you what I think is the best way and encourage you to do it the way I think is the best way, but whatever works for you, works for you. Let's look at something like this. What if I had the integral? Yeah, let's make it fun. From 0 to pi over 3. Let's be smart about this, James. Yeah. Sine of, let's just be sure, sine squared of x over cosine of x dx. So in a problem like this, it's not always super clear if it's better to let u be the sine or the cosine, because essentially either choice, the other one is the derivative. The derivative sine is cosine. The derivative cosine is essentially sine. It's negative sine. But again, we can always adjust for a coefficient, whether it's 3 or 1/3 or -1. We can always fix that. So which thing is stuck? Well, they're kind of both stuck. Did I make a dumb problem? Might have been, no, did I make up a dumb problem? I might have a dumb problem. Yeah, if u is cosine, yeah, that's a problem. Let's make that. I don't love that because you guys aren't going to do that. Sorry, I made up a not good problem. Let's fix it. Let's do the integral from 0 to pi over 3 of tangent. Way more fun. What's the integral of tangent? Good question. The point of a question like this, whether it's tangent or cotangent, is that you should write it as a quotient. For tangent, sine over cosine. For cotangent, cosine over sine. And the choice we should make, well, let's see. Most people usually say they would love to pick u equal to sine because it avoids the negative problem. U equal to sine is not the right choice. Let me show you why. If you pick u equal to sine, what's your derivative of sine? So let me point out that you have du equal to cosine of x times dx. Let me ask all of you, in my integral, do I have cosine of x times dx? I definitely do not. I have 1 over cosine times dx, which is a totally different animal. If you write this out, you can think of this as sine of x times 1 over cosine of x times dx. Or if you prefer, sine of x times cosine of x to the -1 times dx. But we definitely do not have that. So instead, we make the other choice. It's almost always one or the other. So if we let u equal cosine of x, we're a little sad that we have to deal with a minus sign, but not that sad. Our du dx, our derivative, is going to be negative sine of x. And then adjusting for getting what I want a sine of x times dx. So I'm going to have a multiply both sides by -1. I have a negative du equal to positive sine of x times dx. Cool. So now I'm going to rewrite my integral. Actually, I'm going to rewrite my integral 0 to pi over 3. I'm going to write it back how it was, as sine of x over cosine of x dx. And then I'm going to say, okay, well, the sine of x times dx, that's equal to my -1 times du, or just negative du, whichever way you want to say it. And then my denominator there, that's just u. Yeah, it's not undefined anywhere weird. Oh yeah, improper intervals too. Okay, so I get -1 times du over u. Should I change your limits of integration? If you're talking to me, the answer is always yes. So if u is cosine of x, if x equals 0, u is going to be cosine of 0, which is 1. And I picked the wrong value for the upper one. That's not wrong, it's just the less nice one. If x is, oh no, it's not, it's the nicer one. If x is pi over 3, u equals cosine of pi over 3, which is, it's either 1/2 or √3 over 2. And it is 1/2. Because it's the bigger angle, cosine is the x coordinate, which is the smaller value, and it's the bigger angle in the first quadrant. So here I've got the integral from, now be careful, you have to make sure the order is correct. X equals 0 was the lower limit, so u equals 1 should be the lower limit. X equals, and then the upper limit should be 1/2. And since those are out of order, I'm going to change it to be the integral from 1/2 to 1 of +1 over u times du. You don't have to do that. You could totally just integrate it as is and plug them in the wrong way and still get the same answer. It just looks nicer if we do it this way. I don't want to write negative natural log of u and then plug in 1/2 first and 1 second. I would rather write this and get the natural log of the absolute value of u evaluated from 1/2 to 1, and then get the natural log of 1 minus the natural log of 1/2. And we really should simplify this, because what's the natural log of 1 equal to? 0. So really this is equal to the negative natural log of 1/2, which is the same as the positive natural log of 2. Yes, of course. Okay. So we got about 10 minutes left. I feel like we should spend some time talking about integration by parts, just because methods of integration are flying by. So let's go ahead and spend a little bit of time talking about integration by parts. So here's what I would say the differences between U-substitution and integration by parts broadly. You try to use U-substitution to undo a chain rule. You're seeing that you have a function inside of another function and making that your u. Not always 100%, but that's kind of broadly what the idea is. On the other hand, integration by parts, you're trying to undo multiplication. It actually is kind of a reverse product rule, to be perfectly honest. So you're looking for integrals that look more like just things multiplied together and trying to figure out what to do with that. So let me show you an example. Let me show you a non-example, actually. Let's say I wanted to find the integral of 2x times cosine x dx, the indefinite integral. Let me tell you what it's not. It is for sure not equal to x squared times sine of x plus c. And the reason it's not is because of the product rule. If you take the derivative of x squared times sine of x, I'm going to leave off the plus c because the derivative is not 0. You're going to get product rule 2x times sine of x plus x squared times cosine of x. And that for sure is not equal to 2x times cosine of x. So the important thing to know here, and it is important because I've seen people make this mistake over and over and over again over the years, is that when you find the integral of a product of two functions, it is almost never equal to the integral of the first function times the integral of the second function. which is what I did for that there, right? The integral of 2x is x squared. The integral of cosine is sine. So I said, oh, can we just multiply the results together? And the answer is definitely not. And I don't think I have time today to really delve into explaining the entire integration by parts, how like it's how it's derived. I kind of want to, but I shouldn't. So I'll tell you, here's the idea. No, I can't not. I'm gonna say it real quick. So product rule. If you take the derivative of u times v, you get the derivative of u times v plus u times the derivative of v. And now I'm going to anti-differentiate both sides. When I anti-differentiate a derivative of something, what do I get? Sure. So let me ask you, if I took the derivative of x cubed, what would I get? Right. What's the antiderivative of 3x squared?
3x cubed, x.
Over 3, which is just x cubed. We got back to where we started. The antiderivative of the derivative is just the thing you started with. So if I take the antiderivative of that, I'm just going to get u times v. On the other hand, the same thing is not true over here, right? This is not just a derivative of something. This is some other stuff. So what I'm going to write here is now I'm going to change my notation up just a little bit. I'm going to write the derivative of u as du. So I'm going to write this as the integral of v times du plus the integral of u times dv. And then what we do is we isolate this. So we're going to say that the integral of u times dv is equal to u times v minus the integral of v times du. And that is the setup for integration by parts. Okay, here's the plan or the idea. The idea is you're starting with this. We're given some integral. And your job is to look at the integral and decide which part's going to be u and which part's going to be dv, so that when you rewrite it as this expression over here, the integral is simpler. So let's look at this example we've got here. If I'm trying to do, that'll look that good. Sure. So if I'm trying to find the integral of 2x times cosine of x dx, I'm going to pick u equal to 2x. And we'll talk more later about how you know what to choose u equal to. But the reason I'm picking u equal to 2x is because when I take its derivative, it gets simpler. Du is equal to 2 times 1 times dx. And then after you've decided what u is equal to, you have no more choices. V has to be everything else that is multiplied by u. So if my u is equal to 2x, my dv has to be the entire rest of the integral, including the dx. So our dv, is equal to cosine of x times dx, and v is the antiderivative of dv. What's the antiderivative of cosine? The derivative of cosine is negative sine. The antiderivative of cosine is positive sine. But here's what I'll point out. Your choice for dv should be something that that is not terrible to anti-differentiate and doesn't really get more complicated when you anti-differentiate it. And cosine and sine are essentially the same function. So if you go from one to the other, you're not really getting more or less complicated. So now check this out. We're going to write this integral, the integral of u times dv. It's going to equal, well, I'm going to use this formula up here and say it's u times v minus the integral of v times du. So I don't know who chose u and v. Like, they deserve punishment because it's easy to make them look too much like each other. So be careful and make your u's look curvy and your v's look sharp. So this is going to give us the integral of 2x times cosine of x dx is equal to 2x times sine of x minus the integral of sine of x times 2 dx. And look, this new thing that we have to integrate, oh sure, is easier to integrate. We definitely know how to integrate 2 times sine, or just really sine. I'm going to ignore the 2. So this is equal to 2x times sine of x minus 2 times the integral of sine. I probably could have just skipped that step and said, I know the antiderivative of sine of x is, was it positive or is it negative cosine? Negative cosine of x plus c, and then I should really simplify this as 2x sine of x plus 2 times cosine of x plus c. And that is the antiderivative of 2x cosine of x. And if you really want to convince yourself, you can convince yourself by taking the derivative of this right hand side. The derivative of 2x sine of x plus 2 cosine of x is equal to, well, for here I have to use the product rule. So it's going to be 2 times sine of x plus 2x times cosine of x. And then the derivative of 2 cosine x is 2 times negative sine of x. And look, the 2 sine x and the negative 2 sine x add to 0, and you're left with 2x times cosine of x. Exactly as we should. If you take the derivative of the antiderivative, you should get back the function that you started with there. You don't ever have to do that. I'm just showing you that so you're like, oh yeah, we actually found the antiderivative of that, and it's equal to 2x sine of x plus 2 cosine of x. Let me throw one more at you. I know we got 2 minutes. Just one more thing here, and I promise. Let's say I want to find the integral of x cubed times the natural log of x dx. Now let's make it from 1 to e. Let's make it exciting. Ooh, this is a time. So here's a time where we're not going to change limits of integration. So we're not doing a U-substitution. We're still, when we integrate using integration by parts, you're not actually changing the variables. No, that's not, oh yeah, sorry. Sorry, this page, it's literally, sorry. If we integrate using integration by parts, even though you're using u and v, you're still writing your integral in terms of whatever variable you use, which is x. So here, when I write this, the choice I'm going to make for u, should I pick x cubed or should I pick natural log of x? Well, which of those is harder to anti-differentiate? Right, we don't know what the antiderivative of natural log of x is yet, although we will next class. In fact, you have to use integration by parts to find it. So we're going to pick u equal to the natural log of x. In fact, if you see a natural log of x and you're doing integration by parts, that is almost always the choice for you. And then dv has to be the rest. It's x cubed times dx. Our du, derivative of natural log of x, is 1 over x dx. Our v is the antiderivative of x cubed, which is x to the 4th over 4. So now we're going to rewrite this. It's going to equal u times v, so the natural log of x times x to the 4th over 4, minus the integral of v du, which is x to the 4th over 4 times 1 over x dx. I like to be careful here. U, v, v. The important part here is that you have to simplify this integral here. So this is equal to the natural log of x times x to the 4th over 4 minus the integral, bring the 1/4 out, x to the 4th divided by x is x cubed. And now that's something that is not terrible to find the antiderivative of. It's going to be natural log of x times x to the 4th over 4 minus 1/4 times x to the 4th over 4. And so what I should have said here, because I kind of ignored the fact that it was a definite integral, I should have said, I'm just finding the indefinite integral right now, the integral of x cubed natural log of x dx. And then I go back and say, oh, that means the integral from 1 to e. And I really would actually say you should do definite integrals using integration by parts this way. Do all the integrating without the limits of integration. And then as your final step, go back and write the definite integral. Here's your antiderivative. the natural log of x times x to the fourth over 4 minus x to the fourth over 16. And then you're going to plug in from 1 to e. So you're going to get the natural log of e times e to the fourth over 4 minus e to the fourth over 16 minus the natural log of 1, which is 0, times 1 to the fourth over 4 minus 1 to the fourth over 16. And yes, you could simplify that, but it's 301, so I should stop talking. I'm gonna simplify it, but you can go. So there's your final answer if you want to write it that way. Cool. We'll talk more about these things and I guess partial fractions on Friday.